Preparing for SRE at GitLab interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you define SLIs, SLOs, and SLAs for a GitLab service? An SLI measures a user visible behavior, such as successful repository pushes or request latency. An SLO sets the target, perhaps 99.95% successful pushes over 30 days. An SLA is the contractual promise, usually with consequences, so it should be less ambitious than the SLO. I would validate indicators against real customer journeys, publish burn rate dashboards, and use the error budget to balance feature delivery with reliability work. While answering, distinguish measurement, internal reliability targets, and external commitments. Discuss availability, latency, error rate, user journeys, error budgets, and choosing indicators that reflect customer impact. Question 2. How would you design an error budget policy for GitLab's engineering teams? I would calculate the budget from the SLO and measurement window, then define actions for normal, fast, and catastrophic burn. When a team exhausts its budget, risky releases pause while engineers prioritize remediation, capacity, or automation. Exceptions require documented risk and leadership approval. The policy must remain blameless. The budget is a decision tool that makes reliability trade-offs explicit, not a mechanism for punishing teams after incidents. Make sure to cover budget calculation, burn rate alerts, release controls, exceptions, shared ownership, service criticality, and how the policy encourages learning rather than punishing teams. Question 3. Describe your approach to responding to a production incident. I first confirm impact, declare an incident, and assign an incident commander, communications lead, and technical owners. I stabilize the system through rollback, traffic reduction, or feature disabling before pursuing root cause. Updates should state known facts, uncertainty, and next actions at a predictable cadence. After recovery, I verify SLO health, preserve evidence, and write a blameless review with measurable corrective actions and owners. In your answer, talk about detection, incident command, mitigation before diagnosis, communication channels, customer impact, escalation, evidence preservation, recovery validation, and a blameless post-incident review. Question 4. How would you build an effective monitoring and observability strategy for GitLab? I would instrument the request path with latency, traffic, errors, and saturation metrics, then add structured logs and distributed traces using a shared correlation ID. Alerts should represent customer symptoms or rapid slow burn, not every internal fluctuation. Dashboards would connect ingress, application, database, queue, and dependency behavior. I would control cardinality and retention costs while ensuring responders can move from an alert to actionable evidence quickly. Be sure to mention metrics, logs, traces, high cardinality dimensions, symptom-based alerting, dashboards, correlation identifiers, retention costs, and observability from the customer's perspective. Question 5. What makes an alert actionable, and how would you reduce alert fatigue? An actionable page identifies a likely customer impacting problem, has a clear owner, and provides enough context to begin mitigation. I would page on slow burn or severe saturation, while sending lower-risk anomalies to tickets or dashboards. Grouping related alerts prevents floods, and runbooks should include safe first actions. I would regularly review pages, remove non-actionable rules, and track false positives, acknowledgements, and recovery outcomes. Focus on severity, ownership, runbooks, symptoms, thresholds, deduplication, inhibition, paging versus ticketing, alert review, and measuring false positives and response value. Question 6. How would you perform capacity planning for a rapidly growing GitLab workload? I would model demand using repository activity, C job volume, API requests, storage growth, and seasonal patterns. For each critical component, I would identify saturation signals and a safe operating threshold, then maintain tested headroom. Forecasts should include dependency limits and failure scenarios, not just average growth. I would load test representative workloads, automate scaling where appropriate, and review prediction accuracy after major traffic changes. Discuss demand modeling, leading indicators, resource saturation, performance testing, headroom, scaling limits, dependency capacity, cost, and validating forecasts against production behavior. Question 7. How would you design a highly available GitLab service across multiple regions? I would begin with RTO and RPO because they determine the architecture. Stateless application traffic can use multi-region routing, while databases require carefully chosen replication and consistency semantics. Active-active improves utilization but increases conflict and operational complexity. Active-passive is simpler but can fail over more slowly. I would isolate regional dependencies, automate health-based routing, document data loss behavior, and rehearse failover rather than trusting diagrams. Cover failure domains, active-active versus active-passive choices, data replication, consistency, routing, failover automation, recovery objectives, regional dependencies, and testing realistic regional outages. Question 8. Explain how you would define and test disaster recovery for GitLab. Disaster recovery starts by documenting critical services, dependencies, RTOs, and RPOs. I would create encrypted, immutable backups and test restores into an isolated environment, including permissions, secrets, databases, and object storage. A runbook should identify decision makers and sequencing. Quarterly recovery exercises should measure actual restoration time and data loss, expose gaps, and produce owned follow-up work. A backup that has never been restored is only an assumption. In your answer, include RTO, RPO, backups, restore validation, dependency inventory, recovery procedures, access controls, communication, game days, and evidence that recovery objectives are actually achievable. Question 9. How would you troubleshoot rising latency in GitLab's API? I would verify the latency increase by endpoint, percentile, region, tenant, and time window, separating broad impact from one pathological path. Then I would correlate deployment history with traces, database timings, cache hit rates, queue depth, and resource saturation. If a recent change is suspicious, I would roll it back while continuing evidence collection. After mitigation, I would compare P95 and P99 latency against the SLO and add regression coverage. Make sure to cover symptom confirmation, percentile analysis, recent changes, traces, saturation, database queries, cache behavior, dependency latency, rollback, and validating the fix against user-facing SLOs. Question 10. What Kubernetes reliability risks would you watch when operating GitLab workloads? I would watch for incorrect resource requests, memory pressure, pending pods, probe misconfiguration, eviction, and insufficient disruption budgets. Workloads need graceful shutdown so deployments do not drop active requests. Horizontal autoscaling must use meaningful signals and have cluster capacity behind it. I would isolate critical workloads when needed, monitor control plane and storage dependencies, and upgrade incrementally with rollback plans. Kubernetes automates placement, but it does not guarantee application reliability. Discuss resource requests and limits, probes, disruption budgets, autoscaling, scheduling, cluster capacity, noisy neighbors, control plane dependencies, graceful shutdown, and safe upgrade practices. Question 11. How would you make GitLab CI/CD deployments safer and more reliable? I would build immutable artifacts once, test them through progressively more production-like environments, and deploy with canaries or small cohorts. Feature flags separate code deployment from user activation, allowing rapid disablement. Database migrations must support both old and new application versions. Automated health checks should gate promotion, while rollback remains tested and fast. I would measure deployment failure rate, lead time, recovery time, and customer impact rather than optimizing speed alone. Be sure to mention immutable artifacts, automated tests, progressive delivery, canaries, feature flags, approvals, rollback, database compatibility, deployment observability, and separating deployment from activation. Question 12. How would you handle a database migration with zero or near zero downtime? I would use an expand and contract process. First, add the new schema in a backward-compatible way, then deploy code that can read both versions and gradually backfill data in small batches. After validating counts, correctness, and replication lag, I would switch reads, enable writes carefully if necessary, and monitor performance. Only after all clients migrate would I remove old fields. I would avoid assuming schema rollback is as easy as application rollback. Focus on expand and contract migration, backward compatibility, replication lag, locks, batching, observability, rollback limitations, dual reads or writes, and validation before removing old schema elements. Question 13. How would you manage an unreliable third-party dependency used by GitLab? I would define a strict timeout based on the user journey, then use bounded retries with exponential backoff and jitter only for safe, transient failures. A circuit breaker and bulkhead prevent one dependency from consuming all workers. Where possible, I would cache stable results or degrade gracefully, such as disabling a non-essential integration. I would monitor dependency-specific error and latency budgets, coordinate escalation, and ensure retries cannot amplify an outage. In your answer, discuss timeouts, retries, exponential backoff, jitter, circuit breakers, bulkheads, caching, graceful degradation, dependency SLOs, and avoiding retry storms. Question 14. What is a good approach to preventing and responding to cascading failures? Cascading failures occur when overloaded components pass pressure downstream until the whole system collapses. I would bound queues, enforce timeouts, isolate worker pools, apply backpressure, and shed low-priority work. Circuit breakers prevent repeated calls to unhealthy dependencies, while admission control protects core operations. During incidents, I would disable expensive features and reduce traffic deliberately. Load tests and failure injection should verify these controls under realistic overload, not just normal capacity. Cover resource isolation, bounded queues, load shedding, backpressure, timeouts, circuit breakers, admission control, dependency graphs, graceful degradation, and testing overload behavior before production incidents. Question 15. How would you investigate and reduce C pipeline reliability problems? I would segment failures by project, stage, runner type, operating system, and cause, separating flaky tests from runner, network, dependency, and product defects. Queue time and utilization reveal capacity problems, while reproducible logs identify execution issues. I would quarantine and fix flaky tests rather than normalize retries, use deterministic environments, and improve caching carefully. Dashboards should track success rate, rerun rate, queue latency, and time to recovery for each failure category. Mention pipeline success rate, queue time, runner capacity, flaky tests, dependency failures, artifact handling, caching, reproducibility, ownership, and distinguishing infrastructure failures from product test failures. Question 16. How would you use infrastructure as code while minimizing operational risk? Infrastructure as code makes changes reviewable, repeatable, and auditable, but it can also automate a large mistake. I would store code in version control, protect state, run formatting, validation, security policies, and plans in C, then require review before apply. Changes should be small and observable, with drift detection and ownership. For destructive or irreversible operations, I would add explicit approvals, backups, staged rollout, and a documented recovery path. Be sure to cover version control, code review, plan and apply separation, state security, drift detection, modules, policy checks, small changes, rollback strategy, and handling irreversible operations. Question 17. How do you decide whether to automate an operational task? I prioritize automation when a task is frequent, repetitive, error-prone, or performed during stressful incidents. Before coding, I standardize the procedure and define safety checks, permissions, observability, and a clear failure mode. High-risk actions may need human approval or a dry run. I measure success through reduced toil, faster recovery, fewer mistakes, and adoption. Automation that merely hides complexity or creates an unmaintained script is not reliability engineering. Discuss frequency, risk, toil, complexity, standardization, observability, safe failure, human approval, maintenance cost, and measuring the reduction in repetitive operational work. Question 18. How would you conduct a blameless post-incident review at GitLab? I would reconstruct a factual timeline from alerts, deploys, communications, and system evidence, then describe customer impact and recovery clearly. The discussion should examine how systems, processes, and incentives shape decisions, rather than identifying a person to blame. Actions must be specific, prioritized, owned, and tracked to completion. I would share the review asynchronously for GitLab's distributed teams, invite questions, and look for patterns across incidents. Focus on timeline, impact, detection, contributing conditions, decision context, system design, psychological safety, actionable remediation, prioritization, ownership, and sharing lessons across remote teams. Question 19. How would you balance reliability, delivery speed, and developer experience in a remote organization? I treat reliability and delivery speed as connected outcomes, not opposing goals. Platform teams should provide paved roads, self-service deployment, useful defaults, and clear documentation so product teams can operate safely without becoming infrastructure specialists. Error budgets create an objective trade-off when reliability declines. In a remote organization, asynchronous runbooks, written decisions, and transparent ownership reduce coordination cost. I would measure customer SLOs alongside lead time, deployment frequency, toil, and developer friction. In your answer, cover shared ownership, paved roads, self-service tooling, error budgets, documentation, asynchronous communication, cognitive load, platform standards, and measuring both reliability and developer productivity. Question 20. Design a reliable GitLab service for repository pushes and C job triggering. I would accept authenticated pushes through stateless API nodes, validate them, and durably record repository metadata before acknowledging success. C triggering would use an idempotent event and durable queue, allowing independent workers to schedule jobs and retry safely. Repository storage and metadata need replication across failure domains, while queue backpressure protects the API during runner shortages. I would expose end-to-end latency and success SLIs, isolate noisy projects, and test zone failures. Discuss request handling, authentication, idempotency, durable queues, repository storage, C scheduling, retries, backpressure, consistency, observability, multi-zone failure, and protecting the user-facing path. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.